Section 3. The Fourier Transform. You are probably already familiar with the Fourier transform between the time domain and the frequency domain. Suppose we have a time domain waveform, f of t. By taking its Fourier transform, we can decompose it into its frequency spectrum, f of omega, using this formula. This is the forward transform. And by superposing those frequency components, we can recover the original time waveform. This is the inverse transform. In this lecture, we use the convention in which the forward transform contains exponential of minus j omega t, and the inverse transform contains exponential of plus j omega t. This choice is common when we use exponential of j omega t as the time factor, for example, in circuit theory and electromagnetics. So we define the transform pair as these formulas. We also write these transform using the symbol calligraphic f as an operator. Now, a natural question is this: does the inverse Fourier transform really recover the original function? To see this, we start from the inverse transform, but first we truncate the omega integral from minus nu to nu, and then take the limit as nu goes to infinity. Next, we substitute the formula of the forward transform. At this stage, we have a double integral with respect to t prime and omega. Here, t prime is just a dummy variable, so we use a prime in order to distinguish it from the final variable t. Then we change the order of integration and integrate with respect to omega first. Strictly speaking, we need to prove that the interchange is possible. However, in this lecture, we do not consider such mathematical strictness, and it is sufficient to note that it is possible when the integrand is bounded. The omega-dependent part is exponential of j omega t. An exponential of minus j omega t prime, so we can write them together as shown here. Integrating this expression from minus nu to nu, we obtain the result in terms of a sine function, and this is exactly the differentiable representation of the delta function that we discussed earlier. So in the limit, it becomes delta of t prime minus t. Then the remaining integral with respect to t prime is simply the integral of f of t prime and the delta function of t prime minus t. Therefore, by the property of the delta function, the result is f of t. So we confirm that the inverse Fourier transform indeed recovers the original function. Now let us look at a concrete example. Consider a rectangular pulse. The function af of t has the constant value 1 over t0 in the width of t0, and it is 0 elsewhere. Its Fourier transform is easy to calculate because the function is non-zero only over a finite interval, and moreover, it is constant on that interval. So we only need to integrate exponential of minus j omega t over this interval, with 1 over t0. Carrying out the integration, we obtain this function, which is also called the sinc function. Here, I would like to note that the value at omega equals 0 is 1, which also corresponds to the area of the original pulse. Now, let us apply the inverse Fourier transform to this spectrum. Using Euler's formula, we rewrite the sine term into two exponential terms. To evaluate these integrals, we extend the integral into the complex plane and use contour integration in the complex omega plane. Write omega as omega r plus j omega I. Then the exponential factor can be separated into an oscillatory part, which depends on omega r, and a decaying or growing part, which depends on omega I. For the contour integral to vanish on the infinitely large semicircle, we must close the contour in the half plane where the exponential factor decays. That means if t plus or minus t0 over 2 is positive, we close the contour in the upper half plane. In this half plane, omega I is positive where the exponent decays. If it is negative, we close the contour in the lower half plane where omega I is negative and the product becomes positive. Also, the singular point at omega equals 0 is avoided by deforming the integral path. If the chosen contour encloses the singularity at the origin, we obtain a residue of 2 pi j. If it does not enclose the singularity, then by Cauchy's integral theorem, the result is 0. Now let us evaluate the two terms. For the first term, which contains t plus t0 over 2, we obtain 2 pi j when t is greater than minus t0 over 2, and 0 when t is less than minus t0 over 2. For the second term, which contains t minus t0 over 2, we obtain 2 pi j when t is greater than t0 over 2, and 0 when t is less than t0 over 2. So the final result changes depending on the value of t. If t is less than minus t0 over 2, both terms are 0, so the result is 0. If t lies between minus t0 over 2 and plus t0 over 2, the first term gives 2 pi j, while the second term gives 0. The result becomes 1 over t0. And if t is greater than plus t0 over 2, both terms give, so they cancel each other, and the result is again 0. Therefore, we recover exactly the original function. In other words, the inverse Fourier transform of the sinc-type spectrum returns the original rectangular pulse. This example clearly shows how the Fourier transform and the inverse Fourier transform work together, and why the original waveform is recovered correctly.